Nothing. Not space. Not stars. Not even the memory of light. What if there was a place where light itself could never escape? Watch closely. A single beam of light drifts into the darkness, and it never comes back. Reveal. A lone astronaut floating in absolute silence, deep space stretching in every direction around her. Ahead of her, something impossible waits, a perfect black circle, wrapped in a glowing ring of gas, heated to millions of degrees, spinning faster than anything in the universe has a right to spin. No sound reaches her. No warning arrives. Space doesn't announce its dangers, only silence, and that perfect, patient darkness. What would really happen if you fell into a black hole? We are not going to answer that yet. Because before we can answer it, we have to unlearn something. Almost everything you think you know about black holes, the sucking, the swallowing, the cosmic monster hunting through the dark, is wrong. Not because you're not smart enough to understand it, but because the real science is stranger, quieter, and far more beautiful than the myth. Tonight, we replace the myth with the truth. Part 1. The death that builds a monster. Every black hole begins the same way, as a star. Not just any star, a giant one, many, many times heavier than our sun. A star that has spent millions of years locked in a war with itself. On one side of that war, gravity, constantly pulling every atom of the star inward, trying to crush it into nothing. On the other side, the star's own nuclear fire, burning at its core, pushing outward with just enough force to hold gravity back. For millions of years, that balance holds. The star shines. It looks peaceful from 100 light years away, but it's not peaceful. It's a standoff, and standoffs end. Eventually, the fuel runs out. The fire at the core dies. And the moment it does, gravity, patient, relentless gravity, finally wins. The core collapses. Not slowly, not gently. In less than a second, an object roughly the size of our sun, 1.4 million kilometers across, gets crushed down into a region only a few kilometers wide. Try to picture that. Take something wider than most of the countries on Earth and compress it into something you could walk across in 20 minutes. Not flattened, not dented, crushed completely, until there is nothing left inside it to resist the crushing. What remains isn't a star anymore. It has no surface, no glow of its own, no solid ground to stand on, even in principle. It is simply a region of space where an enormous amount of mass has folded in on itself so completely that it has changed the shape of space around it. Astronomers have a name for what's left just outside that collapsed core, in the more dramatic version of this story. As the outer layers of the star realize, almost too late, that the core beneath them is gone, they slam inward and rebound in a titanic explosion called a supernova. For a few weeks, briefly outshining every other star in its galaxy combined. Everything you're made of, the calcium in your bones, the iron in your blood, was forged in a moment like this, in the death throes of some ancient star. But at the very center of that spectacular explosion, something quieter and far stranger is left behind. That is a black hole. Not a hole ripped into the universe. Not a tunnel to somewhere else. A place where matter has been pushed past every limit physics once thought existed. If you're enjoying this journey, and you're curious about the hidden science behind our universe, then you're exactly the kind of person Need Beyond was created for. Take a second to subscribe and join us as we explore the biggest mysteries of space, science, and reality itself. One extraordinary question at a time. Now let's keep going, because what happens next is even more incredible. Here is where almost every documentary, every movie, every casual conversation gets it wrong. We picture black holes as cosmic vacuum cleaners, silent hunters drifting through the galaxy, reaching out to swallow planets and stars that wander too close. That image is dramatic. It is also false. Try this thought experiment with us. Imagine, impossibly instantly, Our sun collapsed into a black hole tonight, keeping exactly the same mass it has right now. What would happen to Earth? Nothing. Earth would keep orbiting exactly where it is, on exactly the same path, for exactly the same reason it does today. No spiraling inward, no sudden pull, nothing dramatic at all. Why? Because gravity does not care what shape something is. It only cares about two things: how much mass an object has and how far away you are from it. A black hole with the mass of the sun pulls on Earth with exactly the same strength the sun does right now. The only thing that changes is what happens if you get close enough to touch it, because now there's no fiery surface stopping you from approaching its center. Black holes are not hungry. They are not hunting. They do not creep across galaxies looking for prey. In fact, most black holes spend most of their existence in near total isolation, quietly orbited by whatever happened to be nearby when the collapsing star was still alive. Utterly unremarkable from a distance, invisible against the dark, doing nothing more dramatic than any other massive object in space. They only become dangerous when something drifts across a boundary that almost nothing in the universe ever comes close to. To understand that boundary, we need to understand gravity itself, not as a force reaching out to grab you, as something far stranger and far more elegant. Picture space as a giant sheet of stretched rubber, pulled taut in every direction. Now place a heavy bowling ball in the middle. The sheet curves downward around it, forming a smooth, sloping well. Roll a marble nearby and watch what happens. It doesn't get yanked toward the bowling ball. It simply follows the curve that is already there, because that curve is the only path available to it. That is gravity, not a pull reaching across empty space. A curve built into the space itself. A planet curves space just a little. A star curves it more. But a black hole curves space so extremely that the rubber sheet doesn't just dip. It plunges downward into something that looks, for all practical purposes, bottomless. This analogy has limits, and it's worth admitting that honestly. Real space has three dimensions, not one flat sheet. But the feeling it gives you is true. Nothing is dragging you toward a black hole from a distance, like a rope pulling you in. You are simply following the deepest curve that has ever existed in the known universe. Now picture the largest waterfall imaginable. Rivers pouring in from every direction. The roar growing louder the closer you drift in a small boat toward the edge. Far upstream, you can still paddle back. The current is strong, but it isn't unbeatable. You have options, you have time. But somewhere along that river, there is a single invisible line. Cross it, and the current becomes absolute. No engine is powerful enough to fight it. No amount of strength, no clever trick, no desperate maneuver can pull you back upstream. From that point forward, the fall is inevitable. That line is the event horizon. It is not a wall. It is not a surface you would feel yourself crash into. There is nothing physically there to touch. It is simply the boundary where the curve of space becomes so steep that escaping it would require moving faster than light itself. And nothing in our universe, as far as we currently understand physics, can do that. Cross the event horizon, and by every law of physics we know today, there is no path back. Not slower, not harder, not with more fuel. Simply impossible. And here's the part that unsettles even physicists. From the outside, that boundary looks perfectly calm. No warning lights, no shimmer in space. You could sail straight past it and in that instant, feel nothing marking the moment your fate changed forever. So, what would actually happen if you fell in? The honest answer is, it depends enormously on the size of the black hole waiting for you. Fall toward a small one, a stellar mass black hole, only a few times heavier than our sun, and something horrifying happens long before you even reach the event horizon. Gravity pulls far more strongly on the part of your body closest to the black hole than on the part farthest away. That difference in pull stretches you, slowly at first, then violently into something impossibly thin. Astronomers, only half joking, call this spaghettification. It is exactly as unpleasant as it sounds, and we won't linger on the details. but a supermassive black hole, the kind sitting at the center of entire galaxies, containing the mass of millions or even billions of suns, behaves completely differently. Because it is so enormous, the difference in gravitational pull across your body, right at the event horizon, is far gentler than you'd expect. According to our current understanding of physics, you could cross that boundary and, for a moment, notice nothing unusual at all. No flash, no jolt, no dramatic warning sign. Just the quiet, growing realization that turning back is no longer an option you have. That difference in scale is almost impossible to overstate. A stellar mass black hole might be only 30 kilometers across, which means its gravity changes dramatically over a very short distance. Over the length of a human body. A supermassive black hole, by contrast, can be wider than our entire solar system. Its gravity is just as ferocious overall, but it changes far more gradually across that same short distance. Size, in this one strange case, is mercy. This is where black holes stop being simply terrifying and start becoming one of the strangest ideas in all of science. Imagine a friend watching you fall in from a safe distance through a telescope. To her, you don't fall quickly, you slow down. Every movement stretches out, second by second, the closer you drift toward the event horizon. Your light shifts, dimmer, redder, fainter, stretched out by the same warping of space that's pulling you inward. Eventually, to her, you appear to freeze completely. A faint, ghostly image, forever suspended right at the edge, never quite disappearing, never quite arriving. But from where you are, none of that is happening. To you, time feels completely ordinary. You fall, you cross the horizon. You never feel yourself slowing down because your own clock never lied to you. Only her view of you from far away gets stretched by the gravity sitting between the two of you. This isn't a visual trick for a movie. This is gravitational time dilation. One of the strangest, most rigorously confirmed truths in modern physics. The stronger gravity becomes, the slower time passes relative to someone standing farther away. Near a black hole, that effect isn't subtle, it's overwhelming, and it means in a very real sense that no two observers near a black hole ever agree on what time it is. For most of the last century, black holes were pure theory, predicted by Einstein's equations, never seen, never confirmed. That has changed piece by piece in our lifetime. In 2015, scientists detected gravitational waves for the very first time. Ripples in the fabric of space itself, caused by two black holes colliding over 1 billion years ago, finally washing over Earth as the faintest tremor our instruments had ever measured. For decades before that, astronomers had been tracking stars near the very center of our own galaxy, watching them whip around an invisible point at astonishing speeds. A discovery that helped confirm a supermassive black hole named Sagittarius A star anchors the heart of the Milky Way. Then, in 2019, something once thought completely impossible finally happened. The Event Horizon Telescope produced an actual image of a black hole's shadow, a dark circle silhouetted against a glowing ring of superheated gas, 80 million light-years away, in the galaxy known as M87. There's one more idea worth knowing about: Hawking radiation, a theoretical prediction made by physicist Stephen Hawking, suggesting that black holes might slowly leak energy over unimaginably long stretches of time and eventually evaporate away completely. It's one of the most important ideas in modern physics, because if it's true, it means black holes are not truly eternal. Given enough time, far longer than the current age of the universe, even the largest black hole would eventually shrink away to nothing. But it deserves honesty, not hype. It has never been directly observed. It remains a brilliant, unconfirmed prediction, one of many mysteries still waiting patiently for proof. So, what is actually inside, past the event horizon? Here is the honest answer. Nobody knows. Our equations predict something called a singularity, a point where density becomes infinite and the laws of physics, as we understand them, simply stop making sense. But most physicists suspect that isn't really an answer. It's a warning sign, a signal that our equations are missing something important. Somewhere in that extreme environment, gravity and quantum mechanics, the rules governing the smallest particles in existence, should meet. And right now, we don't have a theory that lets them meet without breaking. Physicists call the search for that missing theory quantum gravity, and it remains one of the greatest unsolved problems in the history of science. Other ideas push even further into speculation. Wormholes, theoretical tunnels that might, in principle, connect one point in space to another distant point, instantaneously. White holes, a mirror image of a black hole, spitting matter outward instead of pulling it in. None of these are confirmed facts. They are the edges of human imagination, tested against the outer limits of what the mathematics will actually allow. But the deepest mystery of all isn't what's hiding inside a black hole. It's what happens to everything that falls in. For decades, physicists believed something deeply troubling, that anything swallowed by a black hole, every detail, every particle, every scrap of information about what it once was, would be lost, erased from the universe, permanently. That idea broke one of the most sacred rules in all of physics. Information isn't supposed to simply vanish, not ever, not even inside a black hole. This became known as the black hole information paradox, and it occupied some of the greatest minds in modern science, including Stephen Hawking himself, for well over 40 years. Some physicists now believe the information isn't destroyed at all, that it might be preserved, encoded in ways we don't yet fully understand, perhaps even hidden somewhere within the faint radiation a black hole slowly emits over time. If that turns out to be true, then black holes may be far less like a cosmic shredder, tearing reality apart, and far more like the universe's most secretive vault. Nothing is ever truly lost, only hidden, waiting for our physics and our imagination to finally catch up. Look up again. Millions of stars, billions of galaxies, hidden among them, scattered through the darkness, countless black holes. Some barely heavier than our sun, others so vast they contain the mass of billions of suns, anchoring entire galaxies together with their gravity alone. And yet, despite everything we've learned, everything we've measured, everything we've finally managed to photograph, the greatest mystery isn't what black holes destroy, it's what they still refuse to reveal. Tonight, when you look into the night sky, remember this. Somewhere in that darkness are places where space bends, time slows, and the rules of reality itself are pushed to their absolute limits. The more we discover about black holes, the more they remind us how much of the universe is still waiting to be understood. Sometimes the darkest places in the universe shine the brightest light on what we still don't know.